Hi guys, and welcome to Learn Extra Live. It is a Tuesday, that means it is physical science, and as you can see, Phil is standing next to me and it's grade 10s. I have done a shout out, said who's joining us, and I see that Lesejo is in. So Phil, tell us, what are we talking about today?
Okay, well, today we're picking up where we left off last week. We started talking about vectors and scalars, and a lot of people were writing in with some really good questions, and we're going to pick up where we left off last week, and we're going to do some displacement, and we're going to compare it with distance.
Okay, awesome. And apparently Phil's told me you need rulers, you need protractors, you need your pens and pencils, and you need to get ready for an awesome show.
Absolutely, I'm going to do just that.
Awesome. Take your little spot. Okay, guys, so you guys know the drill. What you need to do is you need to join us on facebook.com/Learn Extra, or you can chat to us on Twitter @Learn Extra. And as usual, we are giving away a Casio calculator to the best post on the page. And what this can be, guys, either you're helping each other out on the page, maybe you're posting questions, maybe inspirational tips, chips. Obviously, I'm hungry. So don't forget that this community, guys, is for you. It's not just for us, it's for you to start chatting, to learn more, and to learn extra. And a big shout out to Liberty. Thank you guys for making the show possible. You guys rock. Let's get chatting and let's start the show. Phil, take it away.
Thanks so much, Indy. Okay, well, as Indy says, this is an interactive show. You guys are going to be doing some of the work with us. You can't just do this stuff by watching us. I want you to write down everything we say, and what I'm going to be doing is, I know that the grade 12s are quite used to this, is I pose a challenge question. Now, I'm going to ask Indy to pose up that challenge question on the Facebook page. I want you guys to get some pen and paper and start working with that. You're going to need some pens, pencils, some protractors to work through this. Okay, so most of you have guessed that today's topic is displacement and distance. Now, a lot of people have got misconceptions about this. You were kind of confused from last week what the difference between a vector and a scalar was. Now, we're going to try and dispel some of those problems that people have got between displacement and distance. But before we do that, we're going to give you a chance to start working, to start chatting on the page. We're going to post up that challenge question, and here it is. It's quite a busy one. Well, we're almost there. Hang on. There we go. All right, our challenge question for today is up. Okay, now this is a map. Now, I'm going to help you through this map. It looks like a lot of information. It's very difficult to draw down, so I want you to get on the Facebook page and actually take a look there and see if you can't figure it out. Okay, so now I'm looking for the displacement. Let's highlight some of the important information that we've got in this challenge question. I've asked you for the displacement. Remember from last week, there is a difference between distance and displacement. Okay, now I want the displacement moved during a journey. Now, the problem is that I've actually given you an overhead map. Now, this is going inside the challenge question, and I've given you some blocks. Now, these blocks have got measurements. Those measurements are 100 meters by 100 meters. So I hope that you can see that on your screens. I'm pretty sure my producer's got it up on the screen. Each one of these blocks is 100 meters by 100 meters. I've given you a starting point and an end point. Now, you've got to navigate from the start to the end and find me the amount of displacement which has happened during this. I've also given you some other important bits of information, is that there are roads and there are blocks, and you may only travel on the roads. Other important information to note is that I've got a north reference. I'm told that this is a map, and usually maps, you get a north reference on your map, and there it is. So now I've got to find some way to get from my start all the way through to my end. Now, I've given you a few options. Okay, as usual, I've given you a few misleading sort of examples of what to do and what not to do. Option A, 360.56 meters on a bearing of 213. If you're a little bit confused by the bearing number, that's okay. I'm going to dispel that later. So 500 meters on a bearing of 213.7. Okay, there it is, that bearing number. Or those same two options of displacement, except with a different reference to direction, and that was southwest. So options A, B, C, or D. Now, the problem is that a lot of people are just guessing. Grade 10s aren't used to being tested in this way. Now, you can't just shout out on the page, I think it's A, I think it's B, I think it's C, whatever might be the case. You guys have got to explain how you got your answer to get that calculator. Okay, absolutely vital. I'm telling Indy to ignore you. If you're just shouting out your answers, I want you guys to help each other figure out how to do this question. So if I think it's option A, this is why. If it's option B, this is why, so on and so forth. So let me just run you through the important info again. Okay, so we've got our map here. Each one of these city blocks is 100 meters by 100 meters. Each one of these roads in between is going to stretch in between these blocks. Now, I want you to ignore the width of the roads themselves. Not too important for this question. You've got to navigate from the start to the end somehow, and I've got to use the roads to do this. Now, in my traveling from the start to the end, I've got to figure out what the displacement is. Okay, well, the problem is I'm not entirely sure what these words mean. And if you were watching us last week, a lot of people got displacement and distance mixed up. So what we're going to do is we're going to spend a whole lesson making sure that you know the difference between distance and displacement. And that's the first clue to today's lesson. There is a very big difference between distance and displacement. Okay? So get yourselves from start to end, work around on that page, and try and figure out our challenge question. First correct answer, with an explanation, we'll get that calculator. All right, so let's get into our lesson today. Now let's start taking a look at what this word displacement actually means. So there it is in our nice blue writing. I'm just going to make sure that we highlight and make sure that we got all the important information in there. Now, just a little bit of revision from last week. I know that one is a vector and one is a scalar. I wonder if you can tell me if displacement is a vector or a scalar. Now, there's some very important information. Now, last week we took units and quantities to pieces, and I'm going to do the same thing for the next 30 seconds just to make sure that everyone understands what I'm saying. Well, the first thing that I've got is I've got a number, and that is a magnitude. A lot of people really get tripped up by this word magnitude because it's not something that I use in everyday life. So the word magnitude itself means how much do I have. The other thing which I notice is that there's a unit attached here. That unit tells me what I'm measuring. So this tells me that I'm measuring something to do with length. Now there's a third piece of information, and this is the giveaway. I've got a direction over here, and a direction is very important. A direction tells me that displacement is a vector. Now, I've put in a little bit of an explanation as to what displacement is. Displacement is the length from the starting to the ending point. Okay? Now, that should sound familiar because that's something inside the challenge question. Clue number 2, there it is. So from my starting to the ending point in a certain direction. Well, all of those options, A, B, C, or D, have got a direction attached. So that's not one of the ways that you can tell which one's incorrect. So starting to the ending point, I want you to start thinking about that very, very carefully. Now, when I take a closer look at displacement, it looks exactly like distance, but I've got this addition of the direction. That's what makes one of the major differences between displacement and direction. So moving onwards, what I'm going to be doing is I'm going to be showing you the differences on a map. Now, the map looks very confusing, and when I start taking a look at a map, I can start to see starting points and end points. I'm going to be drawing all over this map. Now, I've got a map here overhead of Centurion in the southern parts of Pretoria, and what I'm going to be doing is going to be writing all over our map. Now, the color which I'm going to be using is not the one on the map. I'm not going to be using orange or anything like that. I think green is nice and visible. So I've got a starting point over here. Starting point is Supersport Stadium, and I want to make my way through to the middle of Irene. So there is my ending point. Now, what I'm going to show you is the difference between distance and displacement. Now, if you were in a car, this would be your only option. So what I do is get in my car and I would start traveling various different ways. So that's exactly what I'm going to do, is I'm going to trace out a path. So I start at Supersport Stadium and I start traveling down my first road and I start making my way down there. And what I find is that I can only stick to the roads. So there we go. I've got this path and eventually I make this last turn and I arrive at my ending point. So what I've actually traced out is the route which I'm going to take. And any of you with those fancy phones with the maps on can actually do this for you. A GPS can do this as well. It can trace out the actual route which I take. Now, I'm pretty sure that you can notice that there's several turns along the way and that I traveled a great distance. What I've traced out here with this sort of pink or purple or magenta line is actually the distance traveled. This is the real world distance which I have now traveled. Now, this is not my displacement. What I'm going to do to figure out my displacement is I'm actually going to figure out what was the end result of my action. Now, to do that, what I'm going to be doing is I'm going to be using an arrow to point directly from the start to the end. Let me repeat that. I'm going to start from my starting point and I'm going to go to my end point. Displacement doesn't care how you got there. It's a path which is direct there. Now, you'll notice that I've actually got a ruler attached to here. Now, what I'm going to be doing with that is I'm going to be moving around on this map, and I'm going to be showing you the difference between the distance and the displacement. Now, if I'm just taking these direct paths and these individual turned paths on here, I can actually measure how far I've gone. So now, first thing which I'm going to do is I'm going to measure the distance on my map. Now, of course, this is not a real distance. You would have to scale this up to many kilometers. But what we're going to do is we're going to see if distance and displacement are the same. Now, you can do this with a ruler because these are mostly nice straight lines. So we can go and add these up. So at my starting point, I'm going to put my 0 on there. And I'm going to rotate my ruler around. And let's start measuring. So what I've done is I've started to move. I've moved around about 2 centimeters over there. Then I go over there, and I'm going to find out very quickly that I go a great distance further down there. So I'm adding to my distance. So that's 2, and that's 3.5. Altogether, my distance is adding up quite quickly. So at the moment, I've got 5.5 centimeters. So now what I'm going to do is I'm going to put my 0 back at the next turn, and we're going to measure even more. So we're going to try and measure our distance there. Okay, I'm going to add another 1.5 to that. So now, all of a sudden, I've got from 2, I've added 3.5, so we're at 5.5. Now we're going to add another 1.5. Now I'm already at 7 centimeters on my map. And then the last leg is around about 2 centimeters, and that leaves me with a total distance of 9 centimeters. So I'm going to write this in just to show you the difference between them. So my distance on my map is 9 centimeters. Now let's go measure my displacement, and this is way, way easier. I don't have to take into account all those turns which I took. So let's pick up our ruler, and the way that you measure displacement is where I started from to where I ended up. So what I find is that my displacement is very often much, much shorter than my distance. Sometimes there's an expression in English that says, as the crow flies. So if you were a bird, could you fly this route? Absolutely. You don't have to stick to the roads. So what I'm saying over here is that my displacement on here is 6 centimeters. So let's write that in with a green pen so that you know what I'm talking about. And here is my displacement. So there's quite a big difference between displacement and distance. Okay, I believe you guys are struggling to see the green. So what I'm actually going to do is I'm going to make a little bit of space down here at the bottom and summarize it. So let's see what goes on when we compare the two. So my distance, let's actually catalog it as we go. My distance, I measured a total distance of 9 centimeters. Okay, my displacement, which I actually measured, and let's keep it in green because you guys know what the green is all about, because the green was the arrow directly from the beginning to the end. So there's my displacement, and my displacement I actually measured to be much, much shorter at 6 centimeters. Now, if I was to give this as my final answer in an exam, I would not get my marks. What I've got to do is I've got to give some sort of direction. Now, here's a bit of a problem. How do I give direction directly off a map? And I'm actually going to make a little bit of space in order to do that. So let's just grab our eraser. Let's get rid of all this excess writing on our map. I wish I could do this in real life to my map. And then what we're going to do is let's just move our ruler out of the way. And let's try and figure out how we could describe our displacement on my map. Now, this map is oriented so that I've got a north pointing directly upwards. I know that north is upwards on this map. The question is, how would I describe the green arrow? I'm going to show you exactly how to do that. Anytime you want some sort of reference, you can draw a north arrow directly through the point where you started. So let's do exactly that. I've drawn in a north line. So now that tells me where north is. I've got to now measure out where this is in relation to north. So now if I've got north, which is up there, I want to know how much this angle is from north. If you were watching last week, what you'll remember is that that is actually called the bearing. That's another clue for our challenge question. So if you're busy working with your challenge question, the degrees clockwise from north. So in other words, the same direction as my arrow is the bearing. Our question is, how do I actually measure bearing? If I've drawn this on my diagram, how do I take the bearing? Now, if you've got your protractor with you, and I want you to have your protractor with you, I'm going to be doing this with you. Let's just make our protractor slightly smaller. Let's move it over to our north line. Okay, so now we're going to measure this together. Okay, now you can see that this is not very useful as it is. What I've got to do is I've got to make sure that my 0 line is on the same line as north. So let's just make sure that that's nicely in line, and we're actually going to go and measure. Now don't worry if you can't see all the fine readings on my protractor. What I'm going to be doing is marking them out. So at the moment, I've got 0 degrees on the north line. What I'm going to do is I'm going to rotate it all the way around, and I'm going to find out what the reading is over here. So let's actually try to figure out what that reading might be. If I measure on my protractor, and you should be doing similar things at home when you draw these vectors, I'm actually going to find out that there is 120 degrees from north in a clockwise direction. That tells me that I've got a bearing of 120 degrees. So now when I give my answer over here, I can't leave my displacement over there. What I've got to do is I've got to work with some sort of direction. So I can add to this. I can say 6 centimeters on a bearing, and remember that bearing means clockwise from north, so a bearing of 120 degrees. Now, it's not always going to be that easy a number. Sometimes you've got to calculate, and sometimes you've got to work with slightly more complex numbers. Let's just go through this again, the difference between distance and displacement. Distance takes into account the entire path. Displacement goes directly from start and ends up at a finish line. It doesn't take into account that I had to turn all the way down there. And displacement is almost always shorter than your distance. But there's something else which is special about displacement. It's got a direction. Now, if you're watching last week, now you can use north, east, south, west if it's a map. The problem is what happens if you don't have the cardinal points, you don't have the compass points. We're going to show you how to work with that a little bit later on. Okay, so now if I was to write this green arrow, let's just make sure that this is correct. Let's actually move away our protractor. We're going to use that a little bit later. How would I write in this green arrow? I would say that that is 6 centimeters on a bearing of 120 degrees. Now, a lot of people are not that comfortable using bearing. That's okay. We're going to be working with it quite a few times. I hope that you saw that we could measure this directly off our map. We were quite lucky because the map was already facing north. Always make sure that you know where that is. All right. The last thing which I'm going to be doing with you before we take our first short ad break is I'm going to be giving you a few directions, and I'm going to be showing you how to work with these directions. I'm going to be showing you how to add up vectors. Okay, so what I'm going to be doing is I'm going to give you various directions just as you would to somebody inside a car, and I'm going to ask you to follow them and ask you what the final displacement is. I'm going to show you how to scale them up, how to draw them out, and how to work with these. So we've got our first direction. I'm told from my starting point to go 120 meters east. Now, most of you figured out that it's very difficult to measure out 20 meters, and it is actually a real pain in the butt to do this in classroom, because I've got 20 meters. I don't have 20 meters to measure this out. So what I've actually got to do is find a way to do this on my ruler, and that's a real challenge. So I've got to scale all of these down. I've got to work with my protractor. But what I think we should do is let you write these down. So 20 meters east, 10 meters south, 5 meters west, and I think you guys should work through. And I think we're going to take a short ad break. What do you think?
Let's give you a break, Phil. Hey, we should
Absolutely.
just make Phil work all day. Okay, guys, I see that you've got quite a few answers that are coming in on Facebook to the challenge question. Yolandi and Zon and others that have just placed, just the A, B, C, or D. Guys, please let us know why you have chosen those answers, because if you show us why you've chosen the answers and you show the workings out, you could be winning this awesome Casio calculator. And we'll be going over that at the end of the show. Okay, let's take a break and we'll see you now. Hi guys, and welcome back to Learn Extra Live. It's physical science and we are having an awesome time. Okay, so I know that you've all been watching and you've all been joining us on Facebook. That's facebook.com/Learn Extra. Chat to us. Also at Learn Extra on Twitter. I'm here to help you with anything that you don't understand. So I've told you about the calculator and you guys all know the deal, but I just want to let you know that we've also got a labeler, and this fancy guy labels everything and anything that you would want or what you would need. But this one, we give one a day. So one on Monday and one on Tuesday, and this goes to the ultimate top mindsetter. So you've got to be posting all the time and learning more and inspiring each other, to get this awesome labeler. So what I'm going to do is I'm going to send you back to Phil. Don't forget, if there is anything that you don't understand, please let us know on the page or on Twitter. There's no such thing as a silly question, only the question asked after the test or exam. Okay, Phil? Take it away.
Thank you so much, Indy. Okay, well, you might be asking why I'm holding one of these. This is just a shortened ruler. This is half of a meter rule. Now, the problem that I posed to you before we went away was, how do I get 20 meters and 5 meters and all of these measurements, which I'm measuring inside displacement, onto one of these? Now, there's no ways that I can go measure out 20 meters, especially if I've got to work on a page. The question is, how do I represent 20 meters east using one of these? Now, the answer is I've got to use a scale. I've got to make these much smaller than they really are. Now, if you take out a map, it's not a life-size map. There's no ways that you can have a life-size map. The only life-size map out there is actually the ground that it's mapping. Now, it's impossible to measure these out, as I said, so what I'm going to do is I'm going to put these down and show you how to cram 20 meters onto one of these, and it's really quite easy. Now, working with scaling very often makes my learners very, very nervous, and it doesn't have to be that way. I'm going to show you how to make them smaller, how to make them much more manageable. First thing is I've actually got to choose a scale. What I'm going to do is put that down, and let's get right into this. How do I choose a scale? Well, it depends on how much space you have to work with. You can start with the ones which I give you, and pretty soon you'll start to get a feel for what we're doing. Now, what I'm going to do is I'm just going to shift that slightly to the side, and let's pick our first scale. Now, I've chosen a scale which works very, very nicely for me, especially when we're starting to deal with tens of meters. You'll get an idea why I've chosen this scale in a moment. So what I'm going to do is I've got the scale over here, and I'm going to shift the scale to one side of my diagram. Very often you can put it up at the top or on the side, but I've actually got to show, when I do a vector diagram, I've got to show what my scale is. So at the moment, we're saying that 2 centimeters on my diagram is representing 10 meters in real life. Now that should start to make things a little bit easier. I can fit centimeters onto my ruler very, very easily. I can't fit 10 meters. So what I'm going to do is every time I see 10 meters, I'm going to fit it in by saying that it's 2 centimeters. Okay, well, what then? Okay, well, I'm going to start drawing these things. Where am I going to draw them? In which direction am I going to draw them? Because remember that vectors are all about the direction. So I've picked my scale over here, and I'm going to show you how to pick your own. And we've put it off to the side. How do we actually start to draw out our vectors? So you guys are going to need your pencils, you're going to need your pens, you're going to need your protractor and your ruler all in front of you. I want you guys to get ready. Now I'm just going to go back to my directions again. First thing that we're going to start doing is we're going to take these apart. We're actually going to scale these down because I cannot fit these on the page, as I said. So I'm going to take 20 meters, I'm going to scale it out. I'm going to take 10 meters, I'm going to scale it out. 5 meters, scale it out. Now the question is, how do I actually do these strange ratios? I'm going to show you a few tricks. So what I'm going to do is I'm going to use my scale. I'm going to use my 2 centimeters to 10 meter scale. Now the way to use a scale correctly is quite easy. It's the same way that I use in ratios, but I notice my grade 10s don't really like ratios. I'm going to show you easy ways to work with them. So if I've got 20 meters, first thing I do is I write out my scale. My scale said 2 centimeters makes 10 meters. Now the first one's actually quite easy because I see, okay, well there's 20 meters, you know, there's 20 meters to 10. Okay, that's quite easy. But now what I'm going to do is I'm going to try and figure out how many centimeters would I need to represent 20 meters. So that question mark is the problem. How do I figure that out? And I actually want you to set this out this way. So I've written out my scale over here, and I'm going to show you how to work with the scale properly, because for some reason I even struggled with this in high school. For some reason it just didn't make a lot of sense. I've chosen a very easy scale, so some of you might be saying, oh, why is he using this very complicated method? Scales aren't always that easy. Any of the geographers out there, if you're reading maps, you've got to know how to do scales. Okay, now this is how this method works. What I'm going to do is I'm going to divide this up, and I'm going to draw just like you would in a window. I'm going to draw the dividing lines between them. Now, it depends on what I've got. I've got one side over there. I've got my 20 meters. Now, the way that you work around here, I want to work from here around my ratio to land up in the other side. Now, here's the way to remember this. Now, if you've ever worked with triangles in terms of times and divide, and I've started working with manipulating relationships between R, V, and I. If you've ever worked with a triangle, this is going to be very, very easy. Now here's the rule. If I go over a flat line, that means that I divide. If I go over a vertical line over here, that means that I multiply. And then my very last one will be equals. Let me do that again. If I go over a horizontal line, that means that I divide. If I flip across that way, that means that I'm going to multiply. And I land up with my answer. Let me show you what I mean. So I'm going to write out the calculation underneath this on how to do the scales. So we're going to take 20. Because I'm going over a flat line, I'm going to say 20 divide by 10. And then what do? I go from 10 across to 2. So I'm working my way around to the one that I don't know. And I'm going to multiply by 2. So if we go 20 divided by 10 multiplied by 2, if you do this all together, I get 4 centimeters. Now, just one last check. 2 is to 10 what 4 is to 20. They seem to be in the same ratio. If you simplify them down, they should be in a 1:5 ratio. Now, if all of that seemed like gobbledygook, we're going to do it again. We're going to do it really, really, really slowly. We're going to make sure that everyone can work with a scale. Now, you may not see scales very often, but it's very important that you can do ratios anyway. So this is a useful skill nonetheless. So what I'm going to do is I'm now going to work with something else. Now, 10 meters is a bit too easy. What I'm going to do is I'm going to show you how to work with 5 meters west. Let's scale 5 meters. So I write down my scale first. So my scale over here, my scale is 2 centimeters, represents 10 meters. That's what I started with. Now what you do is you write underneath the relevant one, or whichever one you've got, you write down what you have. So now what I'm going to do is I'm actually going to write this in white to make sure that we can see the difference between the two. I have 5 meters. I don't have the centimeters. So again, I've got to work my way around here. I draw in my cross, and then it becomes quite easy to see what to happen. If I go over a flat line, that means that I divide. If I go over a vertical line, that means that I multiply. So let's try this out. So I'm going to say 5 meters divided by 10, multiply across by 2, and then I land up with equals in terms of centimeters. Let me write this out for you so that you can see everything that's going on. Let's just bring that all into focus. So everything's on the screen at the moment. So I'm going to start out with my 5 meters. I divide it by 10 meters. So there's my ratio first. I multiply by 2 centimeters. And then I find that I've got a really, really short line over here. That means that I'd have to draw a line which is 1 centimeter. So there it is. I've managed to ratio to represent 5 meters in terms of centimeters. And they're in exactly the same ratio as before. So now I've made all of these lines much shorter. Let's actually list them as we go. I want you guys to practice at home using your ratios, using the same scale that we've got. So 20 meters became 4 centimeters. 10 meters is quite easy because 10 meters was my scale itself. So I'm pretty sure that you can guess that 10 meters is 2 centimeters. And then 5 meters makes 1 centimeter. So this is quite easy. All I've done is I've represented a very large distance in real life with quite a small line using my ruler. So now I've used my scale and I've scaled down all my sizes. These are sizes which I can draw on my page. And that's exactly why I wanted you to have a ruler in front of you. I'm going to show you how to draw them and where to draw them and how to measure the end result. Okay, so let's take our information. Let's find out what's going on. So now I've picked my scale, right, and I've written my scale in the right direction. Okay, so now I've got all this empty space to work with. So what I'm going to do is I'm going to make a blank space to draw on. Now you'll notice that inside that blank space, I've actually drawn a cross with a north. Now the reason that I've drawn a north is because I've been given all these directions. I've been given a reference to east. I've been given a reference to south and a reference to west. So now here's where you're going to draw with your pencil. Now what I'm going to do is I'm going to pick a slightly different color to the one which is on there. I'm going to pick green. Now I want you guys to actually draw with a single-headed arrow, and what I'm actually going to do is make sure that that is just single-headed to make sure that this is absolutely correct. Let's make that a slightly smaller line. There we go. Now I'm going to ask you to draw with me. Now when I start drawing, I start at the center of this compass. So if you haven't done this before, that's great. That means that you're learning. Now we're going to draw in our first vector. So I'm going to put my 0 at the middle of this little compass which I've drawn, and this you're just drawing in rough with your pen. So now I've got my ruler over there. Now I'm going to make my first lines. Now the 20 meters east, how did I represent that? Just remember the lengths that we had. We'd started to scale them. I had 20 meters east, then I turned 10 meters south, then 5 meters west. There's a lot of directions and a lot of distances. So let's keep track of them as we go. So now I'm going to draw in my first vectors. So the first one, 20 meters. I'm going to start from 0, and I'm going to draw all the way out to 4. So I've measured out a 4 centimeter line. Now, here's a very good rule to remember. Anytime that I draw in a vector, what I've got to remember is that I've got to write out the value that it represents. So the value that I represent over here is that I've done 20 meters. Now, the reason that I don't have to say east is because I've actually drawn it on a compass itself. So there we go. We've gone 20 meters east. Now, there's a couple of tricks to what happens now. Now you've landed up in a new position. What I've got to do is I've actually got to start afresh from this side. So what I'm actually going to do is I'm going to draw in another tiny little cross. So you can start out from yourself if you want. What I'm actually going to do is, let's represent that with a different color so that you can actually see what's going on there. I'm actually going to draw in a separate cross here. So I hope what you can see is that I've lined up with my original vector. My original vector strikes my new compass over there. And I can start drawing in my new vector over there. So I've now got 20 meters to the east, and I've got to draw in a completely new compass. So there we go. So we've got a new north reference line. Now what I'm going to do is I'm going to add my next vector. So I've got 10 meters south. Okay, so let's grab our rulers and let's draw in a 10-meter line. Now, if you were listening before, we're not actually going to draw 10 meters, but what I'm going to do is at the end of that arrow, I'm going to rotate my ruler around, and what we're going to do is we're going to draw directly down. Now, you guys are going to have to make sure that your ruler is pointing directly south. Now, you might say, how do I do that? Well, east and south are at 90 degrees to each other. You can check this with the protractor if you like, but it's not absolutely vital. So now I'm going to draw in my next one. So there we go, 10 meters south. Let's draw in 10 meters south, and let's see if we can draw that. So remember that 10 meters south was represented by having a 2 centimeter line. Now, I'm just going to move that out the way, because unfortunately my ruler didn't let me have enough space. So let's just make sure that that is nicely in line there. So now I've got this 2 centimeter long line. Let's just measure it. Let's just make sure that I've got 2 centimeters over there. There we go. I've now measured it. It's 2 centimeters. Fantastic. That means that I've represented 10 meters south. You can write in south if you like, but since you've put in a compass there, you can actually see that that is the direction. Now for our last vector. Now just remember that it's a very good idea to actually draw in a new compass if you like, and we can do exactly that if we want. So there we go. So we've got a new compass to start off from, and we've got a new place to start. Now I'm going to draw in my very last vector. I'm going to remove all these compasses in a second just to leave the green lines so that I can actually see what I'm doing. So 5 meters. Let's just summarize what we were doing in terms of lines. The 20 meters was represented by a 4 centimeter line. 10 meters was represented by a 2 centimeter line. There we go. I hope you can see that. Let's just make that a little bit neater because you guys want to read what I'm doing at home. Okay. So now that is a 2 centimeter line. And then the very last one is a 1 centimeter line. So that's what we're looking for. So now what I'm going to do is I'm going to take my ruler and I'm going to draw in the very, very last one. So let's just make sure that we've got our ruler here. There we go. We're going to start at 0 there. And I'm going to rotate around my ruler so that I can draw again. So let's just put that neatly on the middle. It's not quite there. There we go. Let's rotate. And then as soon as it's locked nicely in that direction, I think we are almost there. There we go. And then I can put in my last one. I can put in my last vector, and that is a 1 centimeter line. So there we go. We can start tracing in our 1 centimeter line. Let's just make sure we got the correct one. There we go. A 1 centimeter line. Okay. Now, this is all starting to look a little bit messy, so I'm going to tidy it up for you guys. So what I'm going to do is I'm going to move away these other compasses. You can rub these out if they're made of pencil, and I just want to leave the vectors in place there. So now what I can see is that, let's just make that over there. There we go. Now, of course, you guys can't do this at home, but there's a very good reason I'm doing this. Is because I actually want to show you what happened in the meantime. So I went 20 meters, 10 meters, and then 5 meters. Okay, we're in the last stages. What I want to do now is I want to find what is called my resultant. Now, these are all distances. If I was to walk, distance is the thing that I care about, because I'd walk 20 meters in one direction, I would turn 10 meters in another, and then 5 in another direction. So what I'm actually caring about over here is how much distance I walked. But now what is the end result? And that is my displacement. So what do I do to find my end displacement? Well, I've got to take a look at my diagram and realize where I started and where I finished. So from start to finish is all that displacement actually cares about. All of these distances told me about my directions and the total distance traveled. We can actually add up, and I'm going to show you the difference between my displacement and my distance. Okay, so now if I've got a neatly drawn diagram, how do I find out how much displacement there is? Well, I've still got my ruler on the screen. All that I've got to do is I've now got to measure what my final displacement is. And let's do exactly that. So now I've got my ruler over there. It's a little bit flipped over at the moment, so let's just get that in the right direction. Let's read with our millimeters, and let's bring it into our picture. Okay, now what I'm going to do is I'm going to start it off in the original position. Now what I'm going to do is I'm going to measure how far away we actually land up from our starting point. Now what you might notice is that that is much, much shorter than our original 20 meters. We actually walked backwards and found our position to be slightly different to our distance. Now, that seems a little bit confusing, so let me just elaborate what that means. I'm going to draw in a line which goes from my start to my end. Now, if you're really awake, you'll realize that this line actually represents my displacement. So my displacement is there on the screen as a blue line. The problem is that it's quite difficult to calculate. Can I measure it with a ruler? If I've drawn very neatly and to scale, absolutely. If you've drawn a very neat vector diagram with your directions absolutely correct, yes, you can actually measure this. And I'm going to do exactly that, and I'm going to show you how we can work this all out. Well, from my starting point to my end point, I can actually measure this out in millimeters or centimeters. Since we're working in centimeters, let's work in centimeters over there. So let's just make sure that we measure it absolutely correctly. There we go. So from the beginning to the end, I see that it is around about 3.5 centimeters. Now, there might be some slight errors inside there, so please excuse me if you do spot those. But 3.5 centimeters is over there. Now, the question is, how many meters is that? So now I've measured out 3.5 centimeters, but now I didn't move 3.5 centimeters. Let's just make sure that's correct. I think that's a boo-boo. That is 3.5 centimeters. I'm sure that you're shouting at home and making sure that we're making the correct result over here. So that is 3.5 centimeters. So now I've measured it out with you guys. The question is, what is the real world difference? Well, I didn't move 3.5 centimeters. What I'm actually going to do now is I'm going to turn 3.5 centimeters into a real life distance again. So now let's take this through. Let's actually use our ratios. So there we go. I'm being told that we're running a little bit short, and people are probably sort of bleeding from the brain.
Should we take a break, Phil?
Absolutely.
Okay, that's exactly what we're going to do. And while we're taking a break, I'm going to have Phil have a look over some of the answers that you've posted to the challenge question. I think there's some goodies there. And what we're going to do is we're going to take a little break. See you now. Hi guys, and welcome back to Mindset Learn. This is physics, and we are having an awesome time here on the grade 10 show. So, Mwepone says that she cannot wait for the grade 11 show, but I think it's kind of awesome that you're watching the grades 10 too. Doctor, you're always here. I have to do a shout out to you because we think that you rock, and we think that you are absolutely awesome. Always on the page. So, what we're going to do, Phil, we're going to get straight back to you to learn more, learn extra. Take it away.
Thanks so much, Indy. Okay, well, you guys are probably wondering what type of calculator is in store. If you haven't seen one, this is a really big version of it. Okay, they're really, really awesome. Okay, the Casio calculator up for grabs. Okay, so before we went away for the break and let you guys rest a little bit, I thought we'd give you a little bit of time out. I wanted to turn 3.5 centimeters back into a real life distance. Now, what I've done is I've rewritten my scale, and this is how you guys are going to do it as well. Okay, so now I'm going to take my scale and I'm going to write in the thing which I have. Do I have centimeters or do I have meters? Well, 3.5 sounds like centimeters. I've got 3.5 centimeters. All right, now I'm going to be using that beautiful calculator and we're going to be working out how many meters that is. Just a reminder on how to work with your ratios. If you write them this way, you can make a window out of them. That's a very nice way to do it. Now what you can do, if you flip over this line over here, now we're going the other direction, but the same rule applies. So first I divide, and then I multiply, and then I push equals. So let's do this together. I'm actually going to show you how awesome this is on this calculator. So let's do this together. There we go. Right, we got a little bit of space. We can see what we're doing. Okay, so I'm going to take 3.5 instead of 3.5. There we go. Now I'm going to make it into a fraction. So let's put it into a fraction. And that's the wonderful thing about this calculator. It just does it for you. 3.5, I divide by 2. Now let's make a little bit of space to multiply by 10. So I hope you can see why I'm dividing first by 2 and then multiplying by 10. And then out comes my answer. And I've got to push my S to D button. There we go, changes it back into a decimal. So 17.5 meters. That's great. So what we're going to do is write in my distance over there. So 17.5 meters. Now, I cannot give this as my final displacement. Let's just write down what we know so far. I know the difference between my distance and my displacement. Here we go. So my distance, let's just add up all my distance. This is how far I walked. My distance was equal to 20 meters. Plus 10 meters, plus 5 meters. And by then I was quite tired. So I added all of that together. So I got 10, I got 20, I got 5 as well. Okay, so now I've got 35 meters of distance. Okay, but now that doesn't tell me anything about where I landed up. That's all that distance can do for me. It just tells me I walked 35 meters. Doesn't tell me if I walked 35 meters up the building, down the road, onto the rugby field. It doesn't actually matter. Now, displacement. This is where the useful information comes in. So now distance, if I turn this into something slightly more useful called displacement, we can actually start to write it down in a much more meaningful way. Now let's compare this with the displacement. Remember that displacement is only measured from the beginning right to the end. Okay, so now displacement. Displacement simply is 17.5 meters. But now, you guys at home are smart enough to know that I can't leave my answer this way. Displacement is a vector. Now, I've got my magnitude, I've got my unit, I need my direction. So let's try and figure out what my direction is. And the way that I'm going to do that is I'm going to whip out my handy protractor. Okay, so let's whip out one of those. Now, very lucky for me, I've always got one in the studio. There it is. Let's just make it a little bit smaller. There we go. So now let's put it on the middle there. And let's start figuring out how many degrees from north this is. Now, there's a couple of ways that you can actually give this direction. So now, if I put 0 on north and I start measuring around, I can start to find my displacement. So now, I think that's almost 0. Let's just make sure that it's absolutely precise so that you guys don't get on the line and say, oh, it's not correct. Let's actually measure our degrees. I'm going to make this even smaller. Now, the only reason I'm doing that is so that I can draw a nice line to show you what I'm doing. So I start at 0 degrees over here. And what I'm going to do is I'm going to measure all the way around here to over here. Now, you guys probably can't see this at home, but over there, I'm measuring a degree of 128. So what I'm going to do is I'm going to write that in as a bearing. So now, if you guys are busy trying to solve the challenge question, and I hope you are, I'm going to write my displacement, and bearing is one of the ways that I gave you directions. So a bearing of 128 degrees is inside there. There we go. We've got a magnitude, we've got a direction. That means that I've got a vector. But what I think we should actually do is I think it's time.
Did you see me getting nervous there, Phil?
Absolutely. You thought I'd forgotten.
I had.
Okay. Well, what we're going to do is we're going to put you guys out of your misery. I'm going to be explaining the challenge question to you guys. So let's jump right back to that. Let's go back to our map. Okay, now most of you guys managed to figure out that there is only one way that I can get from the start to the finish in terms of displacement. So what I'm going to do is I'm going to show you that no matter how you actually navigate through here, you're going to travel the same distance.
Phil,
Yeah.
Can I ask you a quick question? Because
Absolutely.
Charmaine's been up on the page. She's posted the answer and
Absolutely.
whatever, what she thinks it is. But I think maybe this might help. She wants to know, what is the difference between displacement and position?
Ah, very
Before we
good question.
start, yeah.
Okay, now a position tells you where you are. It doesn't tell you any distance that you've moved. So a position might be at this position on the graph. Now, a reference to position tells you where you start and where you end. It doesn't tell you that you've traveled anywhere. Now, what I'm going to do is I'm going to use the word position and try and figure out what it means in terms of vectors. So now my starting position to my end position. Let's try and figure out how I get from one position to the other. A position is just a place. So now if I was to say to you, your position is on the couch. Your kitchen is 5 meters from your position. I hope that sort of starts to clear it up, but we're going to use it a couple of times in the way that we describe this. Okay? So what I'm going to do is I'm going to go from that starting position and we're going to start to get distance and displacement. So now I'm going to figure out a route to get from my start to my end. Let's do that. So I'm going to start from my beginning and we're going to turn some corners and let's navigate through the middle. Now, it doesn't really matter which way you do this. What I'm going to find is that I'm going to get a really large distance. Each one of these is 100 meters long. Now, most of you are saying, okay, well, then there's 100, and there's 100, and there's 100. Okay, so that's 300, 400, and 500. What you've done is you've fallen into the trap. What I've done there is I've measured out the distance. This is not the displacement. Now, it doesn't matter. The way that I've designed this is that no matter which route I take, it's going to measure 500 meters. Now, a lot of people say, which way is the shortest way? There isn't one. Whichever way you go through these blocks, you're still going to land up with 500 meters distance. Even if I go around the outside, I go 100, 200, 300, 400, and 500, I'm actually landing up with exactly the same amount of distance. So there is actually no shortcut between a row of two. So it doesn't even matter if you go around the top. You're still going to get a distance of 500 meters. But that's just it. That is just a distance. Okay, so that means that the distance ones are out. So if you answered option B, I'm sorry. That means that you fell into the trap of distance. Okay, now that was a distance. If you answered D, also, that is a distance. Now that leaves us only with two other options. 360.56 now, is it the bearing? Is it southwest? Well, there's a couple of easy ways of telling. What I'm going to do is I'm going to use a nice fat arrow, but first, let's just clean this up. Let's just make sure that everyone can see what I'm doing. Let's just get rid of all this writing, and let's just see what to do from start to finish. So now, if I go from my start to my finish, I'm even going to forget about the 100 meters for the moment. What I'm actually going to do is I'm going to draw a line which goes right from the beginning to the end. And for that, I've saved a nice big fat red line. So now, if I go from the start to the end. Now, if you did this by graphics or if you did this by Pythag, it didn't really matter. I'm going to show you how to do this by Pythag as well. If I start to make a triangle over there, what you'll notice is that I can actually make a right angle triangle out of this. Now, this is one of the ways that you can actually figure out how much vectors are when you add them together. So now I've got two sides of a Pythagoras triangle. One of those sides measures 300 meters, and then the other side measures 200 meters. Now, if I take those two and I find the Pythagoras hypotenuse between these two, you'll find that it is 360.56. So that's where the distance comes from. That's where this length comes from. The question is, how do I figure out this bearing? And this is quite complicated. So what I'm going to do is I'm going to pull up that handy protractor and we're going to start measuring. Now, what you'll very, very quickly find out is that you cannot actually get this to be southwest. So that gives you a little bit of a further clue. Now, this angle is not 45 degrees inside here, and that's why it is not southwest. So I don't know if you can see my protractor, so I'm going to make it nice and condensed and small. What you'll actually notice is that southwest is 45 degrees off from west. And I'm going to show you why this is not the case. So what you can see over there is that this is actually only around about 30 degrees off there. If I measure this angle over here, I find that the angle is much, much smaller. Now the question is, where does the bearing come from? I've immediately told you that this is not southwest. So how on earth did I get to this crazy bearing of 213? How do you go past 180? Well, I'm going to show you. all you've got to do is you've got to realize that you always start from naught. So I hope that you can see that my protractor is now with its 0 on naught. Then what I do is I start again at 180. So now what I mean by that is I'm going to rotate all the way around again. And what I'm going to do is I'm going to add whatever angle I get there to 180. Now if I add that original angle to 180, I find that my total degrees over here is 213.7 degrees. And that is a bearing as well. I'm just going to redraw that because I'm pretty sure we're going to get some questions about that. Is that if I do that, and I've got my final displacement over there, let's just make sure that we draw it in a final color there. My final displacement, remember, was down there. I take 180 over there, and I add it to an extra angle over there, because remember, we start from naught. And this is how to do bearing. I have measured an extra angle over there. And that is how to get my bearing of 213.7. So the correct answer today is A. And I think that's all we've got time for.
I think so too, but I know already that there's a mindset that's jumping up and down on her couch going, I got the right answer, and she knows exactly who she is, and that is Charmaine. You were the first person to get the correct answer in, and not only that, you helped other mindsetters as well. That makes you an awesome mindsetter, so you win this awesome Casio calculator. I'll be letting you know on the page how to get it sent to you. Thank you so much, mindsetters. We'll see you same time, same place next week. Liberty, thank you so much. You guys rock. Thank you for making the show happen. We had an awesome time. Thank you guys. You make it all possible, and have a fantastic day. Bye.